right, friends, here it is, the final question. This is 2018 BC question number 6. It is a series test kind of question. You are guaranteed that when you take the BC exam that there is going to be a series question on there. It's almost always question number 6. Let's see what we can do with this one. The Maclaurin series for the natural log of 1 plus x is given by this series here. X minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus ... You have the generator, -1 to the n plus 1 times x to the n over n plus ... You are given this information. You're not expected to know this information or have it memorized. They've given it to you. Okay. On its interval of convergence, the series converges to the natural log of 1 plus x. Okay? Let f be the function defined by x times the natural log of 1 plus x over 3. This is a new function that looks a little bit like the natural log of 1 plus x, but it's had some work done to it. Okay. In part A, write the first 4 non-zero terms and the general term of the Maclaurin series for f. So f is x times the natural log of 1 plus x over 3. They've given to us an expression for the natural log of 1 plus x. Let's put these things together. So in part A, we know that the natural log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, -1 to the n plus 1 x to the n over n plus ... That is known, that's given to us, and what we need to do now is build an expression for x times the natural log of 1 plus x over 3. So we probably have done this in class, you've seen the videos, you've worked with your calculus teacher on this. We're going to compare the given series to the new series, or the given function to the function that we're trying to build. And one thing that I see is instead of natural log of 1 plus x, I have natural log of 1 plus x over 3. What we're going to do is we're going to do a substitution. In this original expansion, everywhere we have an x, we're going to replace x with x over 3. So that's going to be the first part of the work. Everywhere you see an x, replace x with x over 3, okay? And then once we've done that, we have to multiply everything by x. So we have two things going on. We've got a replacement, and then we've got a multiplication. And I want to make sure that we're doing this very, very carefully. So the natural log of 1 plus x over 3, I'm just doing the replacement, I'm not multiplying right now, is going to be everywhere there's an x, replace x with x over 3. X over 3 minus x over 3 squared over 2 plus x over 3 cubed over 3 minus x over 3 to the fourth over 4, -1 to the n plus 1, x over 3 to the nth power divided by n plus ... Running out of room there. I want to clean this up a little bit. So now I have x over 3 minus x over 3 squared is the same thing as x squared over 3 squared. To divide all that by 2 means I'm going to multiply by 2 in the denominator. Plus x over 3 cubed, well that's x cubed over 3 cubed times that 3. Minus x over 3 to the fourth is x to the fourth. 3 to the fourth times 4 plus -1 to the n plus 1. X over 3 to the n is the same as x to the n over 3 to the n, and then times n plus all that. Now, I know you're all super smarties. You know that 3 squared is 9 and 9 times 2 is 18. If you do that, you're going to miss the pattern. The pattern in the numerator is we have 3 to a power times a number, and the number always matches the exponent. Okay, so 3 cubed times 3 in the denominator, x to the third in the numerator. 3 to the fourth times 4 in the denominator, 4 in the numerator. 3 to the n times n in the denominator, x to the n in the numerator. I want to leave that here. Well, now what happens, I need x times the natural log of 1 plus x over 3. This work we did was to generate the expansion for natural log of 1 plus x over 3. Now I'm going to multiply everything by x. Well, what happens is every one of these fractions, x over 3 gets multiplied by x, the power increases by 1, x squared over 3, minus x times x squared over 3 squared times 2, that's x cubed over 3 squared times 2, plus x times x to the third, that's x to the fourth over 3 cubed times 3, plus, keep on going, negative 1 to the n plus 1, x to the n plus 1, 3 to the n times n, and so on. Now I want to be careful here because I just realized I got a little sloppy and I forgot to multiply this term. So we're just going to have to sneak that in there. We're going to say minus x to the fifth over 3 to the fourth times 4. And that is super important that that term gets included in there because the instructions in part A said to write out the first 4 non-zero terms, 1, 2, 3, 4, and the generator, that's this guy over here with the n. You could list them out as the series as I did here, or you could write the first 4 non-zero terms are blah, the generator is blah, and that would get you both points. So that's 2 points. I know that was just a whole lot of work that we went through in part A, but we got a good start in this problem. Let's keep going. In part B, we're asked to determine the interval of convergence of the Maclaurin series for f. And here's where we're going to have to be really, really careful. They want us to determine the interval of convergence for the Maclaurin series for f. Show the work that leads to your answer. Okay, so first of all, we need to remember that f of x is x times the natural log of 1 plus x over 3. And that was this expression, x squared over 3 minus x to the third over 3 squared times 2 plus x to the fourth times 3 cubed times 3, dot, 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 dot. And then the generator was negative 1 to the n plus 1, x to the n plus 1, 3 to the n times n plus all the terms that come after that. If I'm going to find the interval of convergence, almost always, not always, but almost always, if I'm going to do an interval of convergence, I'm going to use the ratio test, or I'm going to use the root test, because everything is like, I don't have powers of n everywhere. If everything was being raised to the nth power, then I would consider the root test. But instead, I'm going to use the ratio test. And in the ratio test, you're going to evaluate the limit as n approaches infinity of the n plus 1th term, a sub n plus 1, over a sub n. You're going to look at the absolute value of that ratio, and you're going to compare that to 1. Let me back up on that thought. This is what we know. If the limit as n approaches infinity of the n plus 1th term divided by the nth term is less than 1, then what we get is convergence. We don't know exactly what happens if the ratio is equal to 1, but we know that whenever the limit of that ratio is less than 1, whatever x values that occurs for, we get convergence. So let's start there. So we're going to find the limit as n approaches infinity. I need to build the n plus 1th term, the next term. Well, that is negative 1, n, replace n with n plus 1, you get n plus 1, which is n plus 2. X to the n plus 2. Instead of 3 to the n, this is 3 to the n plus 1. Instead of n, you have n plus 1. That's the n plus 1st term divided by the nth term, negative 1 to the n plus 1, x to the n plus 1, 3 to the n times n. That's the expression that we're going to take the limit as n approaches infinity of. It's big, it's ugly, I get it, but honestly, just writing that ratio earns you the first point. Now what you need to do is just some basic algebra to simplify. So let's keep going. We're going to take the limit as n approaches infinity, the absolute value, negative 1 to the n plus 2, x to the n plus 2, divided by 3 to the n plus 1, times n plus 1. I'm dividing by this expression in the denominator. We're going to do a little keep it, change it, flip it, which means I'm going to multiply by 3 to the n times n, negative 1 to the n plus 1, x to the n plus 1. And now this is where we start canceling. You have negative 1 to the n plus 2, you have negative 1 to the n plus 1, negative 1 to a power, negative 1 to a power. The power is greater in the numerator by 1, so what survives is negative 1. I have x to the n plus 2 in the numerator, I have x to the n plus 1 in the denominator. The exponent is larger in the numerator than it is in the denominator. We do have cancellation, and what survives is x. I have 3 to the n in the numerator, 3 to the n plus 1 in the denominator. 3 to the n plus 1, those cancel, and it leaves me 3. The n and the n plus 1, you want to be careful here. These don't cancel. These don't have the same base. So where we are right now is we have the limit as n approaches infinity, the absolute value of negative 1 times x times n divided by 3 times n plus 1. Well, what's happening here? We're taking the limit as n approaches infinity of this expression over here that's in absolute values. That negative 1 that I'm multiplying by, because it's working in absolute values, that's not going to do anything whatsoever. N is approaching infinity. X isn't changing. X is just x. 3 isn't changing, so I want to rewrite this as the limit as n approaches infinity, the absolute value of x over 3 times the absolute value of n over n plus 1. As n approaches infinity, nothing is happening over here with the x over 3. X is going to be constant, it's going to be fixed for a given value of x. What happens over here? The limit as n approaches infinity of n over n plus 1. These are both degree 1. This is n to the first plus 1. They both have a leading coefficient of 1. What happens here is the degrees are the same. You take the ratio of the leading coefficients. All of this is approaching 1. Not equal to 1, but approaching 1. So your final limit is the absolute value of x over 3. By the ratio test, as long as the absolute value of x over 3 is less than 1, we have convergence. Well, we need to keep going with this. The absolute value of x over 3 is less than 1. We're looking for the interval of convergence. Any value of x that satisfies this relationship means that we are going to have convergence for sure. So if the absolute value of x over 3 is less than 1, then it means that x over 3 is less than 1, but it's greater than negative 1. If I multiply everything through by 3, I get, for values of x between -3 and 3, we have convergence. What we don't know, though, is what happens at -3 and what happens at +3. To test the endpoints of the interval, you're going to have to go back to your original series expression, and you're going to have to evaluate that series when x equals -3 and x equals +3. So let's do that. If x equals -3, then my series, I'm going to write this in series notation. So I've got my series, we're going to go from 1 to infinity. We have -1 to the n plus 1. We have x to the n plus 1 power. We have n times 3 to the n. Well, what happens here? Let's clean it up a little bit on the inside. -1 to the n plus 1 times -3 to the n plus 1. The exponents are the same, the bases are different, but I'm multiplying. Because the exponents are the same, we multiply the bases and we get 3 to the n plus 1 over n times 3 to the n. 3 to the n plus 1 in the numerator, 3 to the n in the denominator. I get cancellation, leaving me just 3. And so I have the series n equals 1 to infinity. The terms are all of the form 3 over n. You might not recognize that right away, so let me factor out that 3, which is a constant. And my series is really the sum of 1 over n from n equals 1 to infinity. What we know is that this is the harmonic series. And what does the harmonic series do? The harmonic series diverges. So what this means is that if x equals -3, at x equals -3, f of x diverges. Because really what we have is just 3 times the harmonic series. Harmonic series diverges, our series must diverge at x equals -3. Let's keep going because we still need to test at x equals +3. At x equals +3, our series looks like this. We're going from 1 to infinity, -1 to the n plus 1, 3 to the n plus 1, over n times 3 to the n. Okay, 3 to the n plus 1 in the numerator, 3 to the n in the denominator. Again, cancellation, leaving a 3 in the numerator. And what we have now is we're going from 1 to infinity. We have 3 times -1 to the n plus 1 all over n. Alexa, stop. We can factor out that 3. And we're going from 1 to infinity, -1 to the n plus 1 over n. This is another series that you should recognize. This is not the harmonic series, but it's the alternating harmonic series. And the alternating harmonic series converges. Because the alternating harmonic series converges and our series is just 3 times that, what we have is converges at x equals 3. When I pull everything together, the interval of convergence we knew we had convergence inside the interval -3 to 3. We've established that we have convergence when x equals 3 and divergence when x equals -3. So this is our final interval of convergence. I know we just spent like 10 minutes or more on this one problem, but look at the points. Look at where the points are coming from. If I can find everything and pull it back together. setting up that initial ratio earned you the first point. Simplifying, that's when we get to this x over 3 and comparing that to 1, earns you the second point. They say determining the radius of convergence earns you a third point, but I would say that happened over here when we realized that our interval converges between -3 and 3. That's before you test the endpoints. There's 1 point for testing both endpoints. So that's x equals -3 and the work that we did at x equals +3. That's one shared point for, it says, for considering both endpoints. Not even reaching a conclusion, they say for considering. That's your fourth point. And then finally, determining and stating your interval of convergence. That is the fifth point. So there we are. Part B is huge. That's a huge number of points. And I would encourage you all right now, go back through this problem, maybe do it again, find other problems involving interval and radius of convergence. These are guaranteed questions when it comes to the BC exam. They're always high scoring kinds of, or high point value kinds of questions. All right, let's wrap it up. All right, here we go. Part C. Let P sub 4 of x be the fourth degree Taylor polynomial for f about x equals 0. Use the alternating series error bound to find an upper bound for the absolute value of P sub 4 of 2 minus f of 2. Okay, so what's going on here? Why are we looking at this particular value? F of x is the function x times the natural log of 1 plus x over 3. That was the original function that we were given. P sub 4 of x is the degree for Taylor or Maclaurin polynomial that approximates this function. So in order to build that, we're going to look at the terms that we created in part A. X squared over 3 minus x cubed over 2 times 3 squared plus x to the 4th divided by 3 times 3 cubed. Now there were other terms in that expansion that we created, but because we're looking at P sub 4, we want degree 4. We want no terms bigger than degree 4. All right, so this is P sub 4 of x. This is f of x. P sub 4 of 2 is the approximation or the estimate that the degree 4 Taylor polynomial gives you to f of 2, which is the true value. When I look at the difference between the estimate and the true value, if I take the absolute value, this is the error. It's the difference between my approximation and the true value. And what this question's asking me for is what's the maximum that error is going to be. That's really important when you're generating an approximation. Well, they told us in part C, use the alternating series error bound. Now that must mean that the that number one, we get to use that. They haven't said that we need to show that the conditions have been met. They're just simply saying use that. Well, what happens with the alternating series error bound is that this value here, P4 of 2 minus f of 2, that has to be less than or equal to the next term in my series expansion evaluated at 2. So that has to be less than, what was that next term? It was negative x to the 5th, so in this case, negative of 2 to the 5th divided by 4 times 3 to the 4th. This guy here is your degree 5 term in your Taylor polynomial or Maclaurin polynomial expansion. And it's always true in the alternating series that the difference between your estimate and the true value is it's actually strictly less than, not less than or equal to, less than the absolute value of the next term evaluated at that point I'm trying to approximate. So I can stop here, or you can simplify if you want to. Because we're doing the absolute value, the negative, we don't need to worry about that. 2 to the 5th is 32 over 4 times 3 to the 4th is 81. 32 and the 4 I can reduce, so this becomes 8 over 81. The 8 over 81 is the maximum error between my approximation and the true value. And so what they said was uses the 5th degree term as an error bound. So like knowing to do this guy here and then getting to your final answer, the 8 over 81 is the second point. So grand total of 2 points. Congratulations, the curse has been broken. I get to film part C. Thanks everybody.